In this video, we're going to summarize the connection between a function and a derivative function. On this graph, you see a function. It's a piecewise function broken into three parts that are color-coded. So what we're going to do is graph the derivative of each of those parts. So first off, let's look at the blue section in the middle. I'm going to do all the derivatives in the same color. In that blue section, you can notice a couple of things. Number one, the function, the blue function, is increasing, and it's linear. Those are two things you can identify. Because the function is increasing, as we saw yesterday, that means the derivative must be positive. If I look at what the slope is, you can see, if you just count the sections there, it goes up 2 over 2, so that has a slope of 1, which means that from here until here, the slope is 1. Because when a function is increasing, f prime of x is positive. And remember that when I say when, that means over an interval of x values. So for whatever x values when the function is increasing, during those x values, f prime of x is positive. And we also just said with the derivative of a line, notice how it's 1 the whole time, we call that a constant. So the derivative of a line is a constant. Let's look at that next section, the green section. Describing this section of the function, I would only really be able to use one word there. It is a constant. It's neither increasing nor decreasing. The y value is staying the same the whole time, which means the rate of change is 0. It's not doing anything. So from this x value until it looks like forever, because there's an arrow at the end there, that derivative is simply 0. And that's an important rule. The derivative of a constant is always 0. It doesn't matter what value the constant is. This green line, it could have been way down here, it could have been up here. It doesn't matter. The derivative would have been 0 no matter how high that constant was. Okay, now for the more complicated part, the red part here, we're going to break it down in a couple of pieces. I always recommend looking at this part first. When a function has a horizontal tangent, which is, we see that right here and right here in both of those cases. There's a horizontal tangent there and there. In other words, a relative min or a relative max. At that point, the derivative must be 0. So what I'm going to do is draw those two zeros there, and everything else will connect through. So when a function has a horizontal tangent, the derivative is 0. Notice how I said f prime of c here, because we're talking about at a specific point, not like a whole range of points, but at that specific point, when x is this value and this value, the derivative is 0. Okay, we're going to use the part we said before. The first thing we said, for that, when we looked at that blue function, we said since it was increasing, the function was increasing, f prime must be positive. Well, the same is true here also. The red function is increasing there, which means that its derivative must be positive. And notice how it's increasing and it keeps getting steeper, 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 which means its derivative must be increasing. The function is also increasing, when I say the function, I mean f of x, is also increasing in that interval up until whatever this x value is, which means over there the function must also be increasing. Sorry, since the function is increasing, the derivative must be positive. So that side will look like that. In between those two, the only part I haven't done yet, in between this section, I can notice that the red function is decreasing, which means the derivative must be negative the entire time. It starts out horizontal, so it starts out at 0 and then gets steeper, 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 and then it starts getting less steep. So the derivative is going to have to go down and then back up again. So we know when the function was decreasing in there, f prime of x must be negative in those x values. Of course, f prime of x isn't negative the entire time, but it's negative within that interval. And we also can recognize the same thing we saw in yesterday's activity, that this cubic function, or what looks like a cubic function, the red function, has a quadratic derivative. And even though we don't see it on this example, we can kind of extend that logic. A quadratic derivative would have a quadratic function would have a linear derivative. A quintic function would have a quartic derivative. And we'll see more about that in coming